Okay, thank you. Okay, so this is sort of part 2, but the topic is slightly different, and supposedly in the title is a workshop, but I think there's not much differences between a workshop, a talk, a seminar, as long as we can get something from it. So since many of you have been here before, so I think we can skip the first 2 and then jump into the content for this evening. So today I'm going to introduce some basics techniques or concepts in structural equation model. So the idea is not to teach you how to conduct or fit a structural equation model in 1.5 hours. So it's not possible because I have a module for 13 weeks on the topic of structural equation model. So it's graduate level statistics. So you can imagine there are lots of materials to be covered in a whole semester, and I'm not trying to compress all of them into 1.5 hours, but I've highlighted some of the key ideas that we need to know before we can learn what a structural equation model is. So for structural equation model or SEM in general, it's not a single technique because it's a family of techniques, or more correctly, a family of multivariate techniques, because many of the techniques probably we have learned before, like ANOVA, Ttest, correlation, regression, analysis, MANOVA, canonical correlation. All of them are special cases of structural equation models. What it means is by specifying a structural equation model, all of these models in some way can be analyzed under structural equation model. Of course, we don't need to learn structural equation model in order to conduct a T-test. But understanding the relationship among all of these techniques help us to choose the best or the most appropriate techniques. And in the old days, we sometimes call it least realm models. So nowadays, it's more general just to call it SEM. Okay. So the whole idea of structural equation modeling is to verify our model. So the first step for us is we need to have a formal model for testing. And then after collecting the data will give us some evidence whether our model is consistent with our data. Okay, so we'll go into more details later. And there are a couple of more special cases that we'd like to know. For example, we have confirmatory factor analysis, CFA. So it is used to verify the construct validity of the measurement. And then we also have item response theory. So if you are doing testing, then IRT is very popular. When we are doing GRE tests or standardized tests, then they are using IRT. And these models in some way can be considered as structural equation models. And the most powerful side of the SCM is it can be used to integrate various techniques, even though like in techniques in mixture model, missing data analysis, non-normal data, categorical data. So all of these can be integrated into a single framework. In other words, we can mix and match. For example, you have categorical data and you also have missing data. Then instead of treating them as 2 different techniques, we can use the same model to handle categorical data and missing data. So there's no surprise that in terms of propagation, there are more and more papers using structural equation models. When we look at this figure, it's a bit misleading because all of us know the number of papers are increasing every year. Okay? But if we take this into account, then the pattern are almost the same. So, so the general message is quite popular. But by the way, if you have attended the previous workshop for meta-analysis, for comparisons, there are much more papers published with meta-analysis than in SEM. One speculation or one reason is SEM, structural equation modeling, is more popular in social sciences, while medicine is popular in both social sciences and even much more popular in statistics. In medicine. So there are much more papers published in medical sciences. So in terms of volumes, so meta-analysis is much more popular if you just count the volume. But in the context of social sciences, SEM is also very popular. So many of the techniques that we have learned before, like regression analysis, we are focusing on one dependent variable. The idea of structural equation model is we can handle more than one dependent variable, depending on our research question. If you have done research before, then you can imagine our theories and also our hypotheses are becoming more and more complicated. Instead of just considering one independent variable and one dependent variables, we would like to know how a couple of independent variables and how several dependent variables are interrelated. That's why researchers, especially psychologists, we are interested in proposing models to explain how it works within the system. And luckily, many of these models can be represented by what we call path models. For path models, we are representing, we need to differentiate between two types of constructs. One is observed, the other is latent. If you are in psychology, probably it's not new to you because almost all the psychological constructs are latent. For example, motivation, intelligence, even for performance, they are all latent. For latent variables, meaning that we cannot measure and observe them directly. In order to measure them, we need to rely on some observed or measured variables. But please bear in mind the link between the observed variables and the latent variables are not perfect. In other words, we can't equate our observed variables as latent variables because by definition or by conceptualization, latents can never be observed unless you have infinitive number of measures. Okay, so this is the major link between latent variable and psychological variables. For example, this is a typical model we call confirmatory factor analysis. In this example, you notice there are circle F1. So this circle or ellipse, it represents latent constructs like motivation, emotion, intelligence, depression. So we cannot measure it or observe it directly. In order to measure it, we need to create a couple of variables like x1 to x4. So for example, we may create some items like for depression scale, then we may use items like are you upset today? Are you depressed today? So we need to create a couple of items. But each item is not depression because depression is something we cannot capture directly. In this model, we use direct links to link the latent constructs to the observed constructs. In other words, our observed variables are reflecting the latent constructs. And we will also see some double arrows representing correlation or variances. So there's measurement errors or unexplained variance, okay? Meaning that these variables are not perfectly capturing the underlying constructs. There's something cannot be captured by the latent constructs, so there are the errors or residuals. So the first type of model like this one, it links the relationship between the latent construct and the measurements. So we call this a measurement model. So this is the building block in psychology, because in psychology we are quite interested in how the latent constructs and the observed variables are related. Another model is path model. In this model, there's no latent variables. For example, we may have a couple of observed variables like composite score, and we are interested in how they are related. And in this case, we may hypothesize that the relationship from a variable x to y is mediated by a mediator m, like this one. So we call this a mediator, meaning it is somewhere between the predictor and the outcome variable. And then we would like to see how this works. Okay. So a typical application in intervention of social sciences is we would like to know why it works. For example, if we are doing some intervention, we randomly assign the participants into the control and the intervention group, and then we observe that it helps the participants to reduce the depression. So this is good from a practical point of view, but we would like to ask why and how. So we may want to add some moderators in between this system, the intervention and also the outcome, depression. And then we would like to see whether the intervention necessary to help them to build their self-esteem and then help to reduce the depression. So the mediating variables are very useful to help us to explain how X leads to Y. So by using structural equation models, we can test this quite easily. And then if we move on, there are usually more than one single latent variables. In these models, we have two constructs, F1 and F2, and each of them, they are measured by 3 indicators. And for these models, the idea is X1 to X3, they're measuring a latent construct, and X4 to X6, they're measuring another construct. In psychology, if you're taking psychometrics, then we call this construct validity. So we are interested in whether the items are remeasuring what they're supposed to be. And by using structural equation models, we can test this empirically. And if you look at this model, if you are not careful, then you see they're almost the same. Okay, so students always want to ask, what's the difference between a CFA model and a structural equation models? And the difference, in fact, is quite minor. When there's no direction, so meaning that the latent variables are just correlated, then we call this measurement model, CFA model. Once we have introduced direction, like F2 predict F1, then it becomes a structural equation model. So in other words, structural equation model is a broad umbrella. It includes confirmatory factor analytic models, path models, mediation models, regression models, and everything. As long as we can draw models graphically, and then we can translate them into, let's say if we are using software, then we can translate them into model specification, then we can test the models. So later we'll see more, some examples. And this is another interesting applications. Instead of observing or measuring cross-sectional data, now researchers are more also interested in longitudinal data. In other words, we are measuring the same variables more than once. So in this case, the variable, let's say yi, is measured 4 times. So we have 4 times the same variables is measured at time 1 to time 4. And then we treat them as 4 variables. And under these models, we call it latent growth models, we can analyze longitudinal data quite easily. So if you are taking statistics, then probably you have learned repeated measures. But from a from a statistical point of view, repeated measures just tell us that whether the means are the same. This is not a very interesting hypothesis. We are more interested in how the variables are varying or changing over time. For example, we can quantify as each subject has own intercept and slope, and then we try to see how they change over time. We'll have an example soon. Okay, so let's get back to some more details. So suppose if we are fitting a model, in this model, we are trying to measure motivation. So we hypothesize there are 2 subscales. One is intrinsic motivation, the other is extrinsic motivation. In the conceptualization, we conceptualize them as 2 latent variables, F1 and F2. So we cannot measure and observe intrinsic and extrinsic motivation directly. So what we need to do is develop some items. In here, we have 3 items for each factor. Then we hypothesize the items are just measuring one single construct. Okay, so this is our model. And then we collect some data. So suppose we are quite lucky. We have collected data from 300 participants, and then we can fit this model. Okay, so the major research question under this CFA model is whether this model can be used to describe the data. In other words, whether this model is consistent with our data. So if the model is consistent with our data, we cannot prove that this is the correct model, but we cannot say that this is not a bad model. Okay, so let me frame it in this way. When we are doing SEM, we cannot prove a model, but we can reject a model. So we can tell that this model is wrong because the model is not consistent with our theory. The model is not consistent with our data. However, if the model is consistent with the data, we can't prove that this is the correct model. This is one of the possibility. There may be other models that also fit the data well. Okay. So for SEM, we are using a model fitting approach to see whether our model and data are consistent. So let's suppose this model fits the data well, then our interpretation is this seems to be a reasonable model. That's why when we are doing structural equation model, we are asking for two major aspects of question. The first one is, as a whole, whether this model fits the data. So this is a very generic question. We are asking a very broad question. Just like for this model, we are asking as a whole whether it is correct, so to speak, whether the data is consistent with it. Okay. We don't care about the details. We don't care about the individual paths. We just want to see as a whole whether this is a reasonable model. But this is not sufficient because if we know that the model as a whole fits the data, the next question is, what are the path coefficients? How good the items are? So that leads us to the second question. We will need to look at the individual parameter estimate, the factor loadings, the factor correlation. So that's why if we are learning structural equation models, we are learning two types of model fit. The first one is more general. We are asking as a whole whether this model is consistent with our data. For the second type of question, it is more specific. We try to ask each path whether it is statistically significant. Okay. So this leads us to a more technical question. So we need to look at this from a more macro perspective. First of all, if you have done research or applied statistics before, then let's say Ttest, correlation, regression, are you looking for significant result? Yes. Why? Because non-significant results may have lots of potential interpretations. For example, your test is not powerful enough, your measurement is not very good, there are lots of measurement errors. So this approach, all the Ttest, ANOVA, regression, and MANOVA, we are using what we call the reject support approach. It means by rejecting the null hypothesis, it supports your research hypothesis. So the hidden agenda for researchers is we would like to reject the null hypothesis. But interestingly, in structural equation models, we are playing a different game because we are proposing a model. So the model, this model, let's say CFA model, is our null hypothesis. We are not in, so it's a bit difficult for someone who are not familiar with SEM. So in SEM, we are not saying the mean between male and female is the null hypothesis. We are hypothesizing the whole model as our null hypothesis. So if you have learned this, then you don't want to reject your model, your null hypothesis, because by rejecting your model, your null hypothesis, we know that it is not correct, but we don't know the alternatives. It is quite difficult to find the alternative models. So implicitly, for researchers doing SCM, we have the hidden agenda is we don't want to reject the null hypothesis. Okay, so this is what we call the accept approach. It means by accepting the null hypothesis or models, we support our research model. So this leads to some problems for us or for researchers. In structural equation models, there's one statistic, or the common statistic is known as the chi-square test, likelihood ratio test. So the idea is if the proposed model is correct, then the test statistic has a chi-square distribution, so it looks very trivial and easy. All of us know how to interpret the result. After fitting the model, it reports the chi-square degrees of freedom and p-value. If the p-value is more than 0.05, then we reject the model, the null hypothesis. So that's end of the story. Okay, but unfortunately, it turns out that the chi-square test almost reject all models. Okay. So if you propose model A, model B, model C, almost all of them will be rejected. Okay. So as I mentioned, if you recall, if we have rejected the model, then we cannot say this is a good model, but we don't know what alternatives are variables. So lead to the problem, we know this is not the model, but what are the potential models, what are the alternative models? Even if we propose alternative models, this model may also be rejected by chi-squares. Okay. So chi-square is, in fact, it is a badness of fit index. So if the chi-square is large, then it indicates your model is bad. And in the past, many models were rejected by researchers by using the chi-square test. So many SCM users were not happy. Imagine if you are trying to publish a paper and then you're proposing model A, B, C, D, E, F, G, and all of them were rejected. So what can you conclude? You can't conclude, we all know A, B, C, D, E are not correct, that's the end. So it's not acceptable. What's wrong, or what are the problems? So some of them are related to the chi-squares, others are more conceptual. For example, the first one is when we are using a chi-square test, one basic assumption is we assume there's a true model, a correct model. But in social sciences, many of us, even in statistics, they don't believe there's a true model. And even though we draw, or I draw a very nice model like this, I don't believe this is the correct model. I don't believe in reality the models look like this. There are two very clean cluster of items. One are only measuring intrinsic motivation, the others are only measuring extrinsic motivation. Even though when you are directing the items, you attempt to measure intrinsic motivation only, there are some of them may be measuring extrinsic motivation. Okay. So this is just a rough approximation. This is just a tentative model. We don't believe this model is correct, even from the researcher's point of view. So now the question is, if there's no correct model, then why do we continue to use a correct or exact test to test it? Okay, so this is one problem with the chi-square test. George Box, a famous statistician, this is has a very famous quote. Essentially, all models are wrong, but some are useful. Okay, so from researchers' perspectives, we don't mind the models are all wrong. As long as they are useful enough, they can be used to capture or represent the reality. Okay, so this leads us to other problems. For chi-square tests, it has some assumptions. For example, we need to assume the data multivariate normal. And in social sciences, most data, unfortunately, are not multivariate normal. So the chi-square test may not work as expected. There are other issues. For example, if you are familiar with power, so statistical power, if you have large sample size, then the statistical power is larger. If you have a small sample size, then the statistical power is smaller. Then in primary research, like when we are conducting a Ttest, we will be rewarded by collecting more data because the test will be more powerful. We are more likely to reject the null hypothesis. If we are using chi-square in SCM, then the incentive is totally reversed, because if you are collecting more data, it's more powerful, it's more likely to reject your proposed model. So it looks like researchers have an intensive to collect smaller subjects. Okay, so it doesn't sound to be a good idea. So how can we fix it? Unfortunately, in terms of statistics, there's no way to do it because chi-square test is the only correct statistics. Okay, so researchers are moving from chi-square to a slightly different direction. The key change is instead of asking a model to test whether this model is correct, they are asking a different question, whether this model is approximately good. Okay, so this is switch from what we call the exact test to approximate test. In other words, we don't believe our model, our proposed model is correct, strictly speaking. It is just an approximation of the reality. So now it provides some rooms or different directions. And this leads to the development of goodness of indices. There are lots of goodness of indices in the market, and they are measuring different aspects. One of them is the incremental fit indices. It measures the relative improvement. So the idea is like this. Instead of asking, let's say this model, whether it is correct, if you want to ask this question, then we have to use the chi-square test, and then we have all the associated problems. Now we are asking a different question. Instead of asking whether this is the correct model, we are asking how good this model is when compared to another model, a baseline model. So we select one baseline model and use it as the reference. And then we compare the improvement. And for the baseline model, we are usually using a model which doesn't correlate at all. So there's no double error. There's no association among them. In other words, x1 to x6 in the baseline model, they are totally independent. And then we use it as a baseline model, and then now we fit our model. Then by comparing the change, the improvement, then we can calculate some fit indices, and these fit indices indicate how good this model is when compared to the baseline model. Okay. So now you can see we have shifted our focus. When we are using chi-square test, we are asking an absolute question, whether this proposed model fits the data. When we are using incremental fit indices, we are asking or comparing whether this model is better than the baseline model. These two pieces of information can be inconsistent. For example, as a whole, this model is not correct based on the exact test, but it can be better than the baseline model. Okay. So researchers developed something like normed fit index, NFI, and it uses the base rate for the chi-squares as the comparison. Okay. And there are also other improvements like non-normed fit index, TLI, and also later for CFI. So all of these use the baseline model for comparisons. Okay. So in convention, in the past, researchers are asking for 0.9. So if your CFI or TLI are better than 0.9, then the proposed model fits the data quite well. If you use the same meaning, then you know 0.9 means the improvement when compared to chi-square. But of course, now based on some more research, then usually researchers are asking for more. 0.95, 0.96 are quite common. So if you only have 0.9, then it doesn't mean that your model is good. Then the incremental fit indices is one class or one idea of comparisons. We can imagine other type of comparisons. The second type is residual-based indices. So as we have mentioned before, when we are fitting models, we are comparing our data and our model and see whether they're consistent. Just like in regression analysis, we can calculate the residuals that indicate the discrepancy between your data model. And then based on the residuals, we can calculate some fit indices. There are two popular ones. The first one is standardized mean square residual, SRMR. And based on some rules of thumb, usually if it's more than 0.05, then it's quite good. Okay. So this 0.05 indicates the discrepancy between your model and your data. Another type is root mean square error of approximation, RMSEA, is also quite popular. The one attractive feature is we can construct confidence interval on this RMSEA. Okay. So as a rule of thumb, if it is more than 0.05, then it indicates the model fits the data quite well. Okay. And in the range of 0.05 to 0.08, then it's still quite okay. But if it is larger than 0.1, that means it's quite bad. Okay. So the idea of the RMSEA is slightly different from chi-square, because for RMSEA, we are not asking for 0. For 0, it means it's exact. The model and the data are identical. So the chi-square test, in fact, is testing 0. And then now we leave some room, we allow the model and the data are slightly different. And then we expect the discrepancy is more than 0.05. Okay, so what are the typical standard in reporting? It varies, and it's hard to tell because different researchers may have different preferences. So usually a good idea is we need to report more than one goodness of fit indices, and we must report chi-square, degrees of freedom, p-value, and then we also report some residual base, some incremental fit indices. And this is one of the common practice, like we use more than one fit indices to indicate how good your model is. Okay. In other words, we are not focusing on just one fit index. We need to report multiple. If most of them are consistent, then it makes it easier to justify your model. For example, in this sample data, the chi-square test is quite good, the CFI, the RMSEA, SMR. So we need to report a couple of them. And the exact preference may depend on, let's say, the reviewers or the editor's preference, but probably you need to report more than one type of fit indices. The main reason is they are based on different rationale. So some of them may not be consistent. Some of them will be very high, some of them could be very low, because they are doing different types of comparisons. They're not asking the same questions. Okay, so suppose if our proposed models fit the data quite well, that means this is a tentative model. We may want to look at the individual parameter estimates. If you remember in our model fitting, we are using, we have fixed 1 and then another loading 1. So the idea is we use this reference point 1 as a reference point in our analysis. And then now when we compare the model, we can say for the second item, it is slightly smaller than the first item. For the third item, it's also slightly more than the first item. So we put a comparison, a reference point. We are using 1 for the first item, and then all the other items are comparing to this one. This is one way, but it leads to a problem. It is quite difficult to interpret the whole values. So that's why usually when we interpret the individual parameter estimates, we prefer to standardize everything. So if you have calculated correlation before, then you know correlation is a standardized version of covariance. For correlation, the range is from -1 to 1, so we can interpret what it means. Similarly, for the standardized coefficients, we standardize the variables. So now we know this is 0.66, 0.60. So the main advantage is once we have standardized it, then the factor loadings can rarely bigger than 1. Usually it is within 1 or -1. So it makes it easier for us to interpret and see how large they are. So the standardized solutions or this set is quite useful for us when we do the interpretation. And for most programs, they will also report the unstandardized version and the standardized versions. Okay. So the standardized version is mainly for us for interpretation. Then sometimes we may have what we call non-nested model, or let's imagine you propose 4 or 5 models, and then you like to come up with the idea which one is the best, which one fits your data the best. So then in structural regression model, we may use either LKI information criterion, AIC, or Bayesian information criterion, BIC, to do model comparisons. The idea of these two indices is they try to compromise between the model fit and the model complexity. So they are not asking for whether your model are correct. Okay, so they're asking a different question. When we are using AIC or BIC in selecting the models, we are trying to find a model that has a good compromise between model fit and model complexity. It means we want the model to have a good fit for data, and at the same time, it's not too complicated. So we can use AIC or BIC to help us to select the models. So usually a good idea in terms of the research design is before fitting or conducting structural regression models, you come up with a few theoretical based models. You have 3 or 4 models. And then after fitting the models, then you use some indices like AIC, BIC to select which model is the best. And then you also look at the individual model fits, the parameter estimates. So after comparing a couple of models, you can figure out which one is the best based on your data. Okay, so SCM, in fact, is just a combination of path model, or we call structural model, and also measurement models. Okay, so let's look at an example. So this is a classic example in almost all SCM manuals. So we studied the stability attitudes over time. So it's a repeated measure at 1967 and 1971. So they included alienation and relations to background variables such as education and occupations. So there are 2 scales. One is for alienation. It includes a nominal subscale and powerlessness. And for the SCS, Duncan's socioeconomic index and the years of schooling. So this is the model. For SCS, there are 2 indicators, education and SCI. And then for the alienation at 67 and measure 71. Okay. So since we are by convention, time moves from 67 to 71. So that's why the direction is always determined by time. So this is another case of the mediation model. So the idea is SCS affects both the scores at 1967 and 71. Okay, so this is the basic model. And in these particular examples, the same items, powerlessness, was measured at 2 time points, 67 and 71. And also for, I think for the nominal subscale is also measured at these 2 time points. So when we fit the models, we expect these 2 residuals can be correlated. So they are not related to the content. It's simply because we are using the same measure twice. So the residual, the measurement errors can be correlated. So that's why we add the red correlation, okay, on the residuals. Okay. So by fitting this model, the data looks quite good. Okay, so in fact, it's very good. So the p-value is 0.32. So it also is even non-significant. Okay, so all the 3 indices are all quite good. And in this example, if we compare the model without the correlated errors, then the chi-square change is also very large. In other words, it makes sense to include the correlated errors, because by adding the correlated errors, the model fit improves a lot. Okay, so of course, after fitting the model, so if you are working in these areas, in the content, in the substance, then it's up to you how to make sense of the results based on this model. Okay, so then we move on to the last part, which is more interesting and nowadays more popular, is how to model longitudinal data. So in the previous parts, we are focusing on cross-sectional data, or even for this model, we only measure it twice. It is not a truly repeated measures. But nowadays, many researchers are interested in longitudinal data. So we would like to model the longitudinal data over time. One reason is for longitudinal data is more easier for us to draw causal directions. We can tell how X causes Y. Based on the time frame, we can frame it this way. And we are also more interested in intra-individual differences and inter-individual differences. For intra-individual differences, it is the variation within subjects. It means the variation over time. For example, if we are measuring emotion, we don't expect for emotion is always the same. It goes ups and down. So this is the variation. We call it intra-individual differences. The other type is inter-individual differences. This is the differences between you and me across subjects. So by using latent growth models or longitudinal data, we can separate or decompose the variation into in repeated measure. We call it within subject and between subject variation. So it's quite easy to do it. Moreover, we can include study characteristics or samples characteristics, let's say whether they're males, female, their age, and their backgrounds. And then we can include all of this into the modeling. So when compared to more conventional type like repeated measures, there are a couple of advantages. And that's why it makes the repeated measures ANOVA less popular when compared to latent growth model. For example, for latent growth model, we can model each subject's pattern. So we can customize to each subject's model. And another major advantage is it can allow missing data. If you are measuring repeated measures, suppose you have 5 points, but if one at the end, let's say the participant didn't participate in the last measure, then they're missing data. Then you can't use repeated measures unless you do some imputation. But in the context of structural regression model or latent growth models, we can model it without problems. So we can allow complete and incomplete data in the same framework. And more importantly, we can allow what we call time varying and dynamic variables. It means if you are doing, let's say, repeated measures, you are measuring the participants' performance in your lab. Okay, so you are monitoring the performance. And you know that one factors that affect the performance, motivation. Okay, so at the first part, when the participants are doing the experiments, they are quite motivated because it's new, there are lots of stimuli. And then in the second trial, third trial, over time, the motivation drops, and so does the performance. Okay. So we can also measure the motivation at the same time and the performance. And by using latent growth model, we can model and analyze all of this simultaneously. But if we use repeated measures, we cannot, because for repeated measures, we can only handle what we call time invariant predictors. That is either age, educational level, or if you want to measure motivation, then you need to measure motivation before the experiment. And then for that part, the motivation is a fixed score. We can't measure motivation over time and use it in the modeling for repeated measures. Okay. So latent growth model is more flexible in terms of handling the data. And there are 2 types of latent growth models. The first one is what we call unconditional latent growth models. The other type is conditional. For unconditional, the idea is we're trying to describe the pattern. We are not adding any predictors. We just try to see how the subjects or the participant varies over time. By adding predictors, then we like to ask the question, how the subjects or the participants' characteristics affect the patterns. Okay, so let's look at a concrete example. So this is a data set from the children of the National Longitudinal Survey of Youth. So the key dependent variables here is antisocial behavior. So it's measuring from time 0 to time 3. So there are 4 time points. So we measure the antisocial behaviors of children over 4 different time points. And here we have 2 time invariant covariates. The first one is gender. So the question, we would like to see whether the antisocial behaviors of the children are different between males and females. But of course, I think we all know the answer. But let's see whether it's different from our expectation. The other one is the cognitive support of the parents. So it measures whether the children have better support from their parents. If the hypothesis is if they have better support, then they will be less antisocial over time. So the two key research questions is how they change over time, and also what are the predictors. So just like typical research questions. And we use the same structural equation model, the CFA. Okay. But for this model, it's a bit strange to us because it looks like one factor model. Okay. But at the same time, all the factor loadings are fixed at 1. Okay. So this basically means there's a flat line. We are fitting a flat line. There's no change over time. We call this a baseline model. This is not a correct model. Okay. So we are not interested in this model. But by fitting these models, we are asking a question. What is the between subject variation to the within subject variation? So we call this ICC, intra-class correlations. In other words, we would like to decompose the total variation into between subject, that is the variation between subject A and subject B. One is more antisocial than the others, versus the other component within subjects. So the variation over day 1, day 2, day 3, day 4. So we decompose it in the between. So as expected, this model fits the data very bad. Okay. By the way, if it fits your model well, then it could be a nightmare, because it means this model is a well-fitted model. Your data for the participants just a flat line. There's no variation. They won't change. So this is not good. Okay. So the baseline model, if it doesn't fit well, it is a good news, because we are not interested in this model. For these models, we are only interested in the ICC. So the ICC, the calculated one is 0.48, so it's about 0.5. So what it means is for the variation, about 50% is due to the between subject. Okay, some children are more antisocial than others. So this is a between subject factor. The other 50% is the within time. So over these 4 time points, there are variation. Okay, so it's about 50-50. Then the next step, in terms of concept, we can conceptualize us. Let's imagine we just pick up each child. Okay, so we pick one child, and then we fit a straight line. Okay, so in this line, we are using the intercept and slope. So if you have learned or remember the geometry, in order to draw a straight line, we need the intercept and the slope, then we can fit a straight line. Then we do it for each child. So some child, the slope is quite big, so they become small and more antisocial, but for others, it's quite stable. There's not much change. Okay, so there are lots of variation. Suppose if we collect all of these slopes and combine them together, then we have lots of lines. Each line represents the estimate of each child. Okay, so we can see there some of them are more antisocial at the beginning. Okay, and then some of them becomes more or quite antisocial. So there are lots of lines. Okay, when we have lots of lines, it makes sense for us to calculate average line. So we can calculate average intercept and average slope. So the blue line represents the average of all children. Okay. So the idea of latent growth model or mixed effects model is we summarize all of this data, the children's, into these 2 pieces of information, the average intercept and average slope. When we are talking about the average, this is fine. It's already good enough to use the average intercept and average slope. But this is not complete, because let's say on average, the children or most children are becoming more and more antisocial, but there are still lots of variation. Okay, so you can expect just the mean is not good enough. If you have attended the meta-analysis talk, then you know we also need the variance. So Then we need the variance on the intercept and the variance of the slope. Then now we have a complete picture. For the mean or the average intercept and average slope, we call them fixed effects. Then for the variances on the intercept and on the slopes, we call them random effects model. Okay. So the terms look a bit scary, but in terms of concept, it's very straightforward. If we look at the figures, we can also calculate the variance on the intercept and variance on the slope. And then conceptually, they represent the fixed effects and random effects. So the fixed effects tell us the average of all subjects, all children. And then the variances tell us their variation. So let's imagine for the variances to an extreme, if the variances are very, very small or 0, then basically all the lines will merge together, and then there's one single line. But on the other hand, if the variances are very big, then now if you describe there's a positive trend, they are becoming more and more antisocial, then we need to be careful because this is just the average, and then there's a lot of range. Some of them can even be negative. So the fixed effects and random effects tell us different pieces of information. One is the average, the other is variability. And in terms of SCM, then we can use models like this. And if you look a bit scary, then we just need to focus on the so-called the I and S, the latent factors. The I represent the intercept, and the S represent the slopes. In other words, by using this model, we can extract the information of the children, their antisocial behavior, and consider them as latent factors on both the intercept and slope. Then we can estimate the mean, represent the fixed effects, and the variances, which represent random effects. Okay. So there's a one-to-one correspondence between the graphical model and the mathematical models. So usually I like the graphical models because it's easier to comprehend. And then after fitting the models, then we can interpret the fixed effects and random effects. For example, in this case, the proposed growth models fits the data quite well. The CFI, the TLI, all of these fit indices are very well. And then when we look at the fixed effects, for the intercept, it means at the beginning of the project of the measurements, the scores of the antisocial behavior, the average is 1.5. And then the slope is 0.179. It means on average, if you're moving from time 1 to time 2, the children's they are becoming more and more antisocial by 0.179 unit. Okay, so there's a straight line becoming more and more antisocial. And then there are also some variation on the intercept and on the slopes. Okay. So the second part, after finding that on general they're becoming more antisocial, then the next question for us is we try to ask the question why. Why some children they are more antisocial in the beginning and becoming more and more antisocial over time? So a logical question in here, since we have the two predictors for gender and cognitive support, is can gender and cognitive support help us to predict the intercept and slope? Okay. If you still remember in the whole model, when we are fitting models like this, we are summarizing all the trends into two parameters or two key things. One is the intercept and slopes. So now we treat intercept and slope as our dependent variable. So we treat them as dependent variables, and then we put it into this model. So we are using cognitive support and gender as predictor and predict intercept and slopes. So the beauty of SCM is we can just add them as IV or DV, independent variable, dependent variables. It's quite easy. Okay. For example, if you have a different set of questions, you may want to ask, how about after these 4 time points at the end of the project, you're measuring the performance, the academic performance. So you have another variables. Then you like to ask for children who are more antisocial, they're becoming more and more antisocial. Would this affect or predict the academic score? Then you can use I and S to predict the academic score. Okay. So in SCM, it's very flexible. we can treat I and S in this case as either independent variable or dependent variables, or even both. Okay, so we can add this into the graphical model, and we are testing our research hypothesis. So in this case, we are using I and S as the dependent variable, and we are using cognitive support and gender to predict it. So I've skipped all the technical analysis and detail and just present the output, the findings. So in this data set, when we are looking at gender, after controlling parents' cognitive support, it turns out gender is significant in predicting the intercept, but not slope. So what it means is, we are using gender to predict intercept, it is significant, but when we use gender to predict slope, it's not. So the implication is these two lines, they are parallel. In other words, in the beginning, it's quite obvious that boys are more antisocial than girls, but this trend is constant over time. Okay, so it means once boys are more antisocial than girls in the beginning, then they're the same. So over time, boys are getting more and more antisocial, and so do girls, and the trends are the same. It is not statistically significant, just like in these figures. Then how about cognitive support? The conclusion is reverse. For cognitive support, it is not significant in predicting the intercept. In other words, for these three of groups, by the way, in this case, it's similar to moderating effect. We categorize them into +1 standard deviation, -1 standard deviation for plotting only. In the beginning, there's not much difference. All of them have the same starting point for these three, regardless of the level of your cognitive support. But over time, you notice that for children with better cognitive support, they tend to be less antisocial. But if they don't have cognitive support from their parents, they tend to be more antisocial. Okay. So by fitting this model, then we can answer these two research questions. Okay. So it's quite easy and straightforward. If you have other variables, we can put it into the model. Okay, so to conclude, we have demonstrated for structural equation model, it can be applied as a cross-sectional design and also for longitudinal design. For cross-sectional design, usually we are focusing on two parts. The first one is for the measurement part. We are looking at how the latent variables and the items are related, the so-called construct validity. And at the same time, we can also hypothesize the directions of the model. And as you can see here, the directions are just based on your theory. So there's not much limitation. You can add more than 2 variables, 3 variables into your models, it's fine. Okay. The second part, or the second focus of the structural equation model is how to handle longitudinal data. So in this case, the idea is very straightforward and simple. Instead of treating it as a longitudinal data, we treat it as different variables. So for example, in this case, we are measuring the same variables 4 times. Okay, so the antisocial behavior at time 0, time 1, time 2, and time 3. In this framework, we just put them and treat them as 4 different variables. And then we can test some models like this. And then it is mathematically equivalent to the so-called the mixed effects model, multi-level model in analyzing it. So it's a very convenient framework. And we don't have time to talk more about the advanced techniques like how to handle missing data, non-normal data, and categorical data. For example, we can do mix and match. Instead of having continuous variable, you may have binary variables. Let's say you have variables indicating whether the children are antisocial, just yes or no. Okay, so you're measuring, and then if they have some antisocial behaviors, then the parents may take yes. If they don't have any antisocial behavior, then no. Then we can also use the same model, the latent growth model, but we just change the analysis a bit by telling the program, knowing that you are now analyzing the binary data, then almost all the techniques are the same. Or if you have non-normal data, for example, if you're measuring some variables that you know for sure it won't be normally distributed, then we can handle it by using what we call the robust statistics. So, and then the other case is missing data. In this example, we don't need to assume that we are measuring the antisocial behaviors across all the 4 time points. If they are missing data at time 1, time 2, time 3, is fine. But of course, in the presence of missing data, it will affect the power of the test, because when they're missing data, it means they are missing information. It won't be as good as complete data. But we don't need to delete or throw away all the missing data. So that's the main attractive point of using the structural equation model. Okay, so I think I will stop here and to see what question you have and comments. Okay, thank you.